Okay, so welcome to the first video in Chapter 8. So in Chapter 8, we're going to return to hypothesis testing. So I need to pause, copy, and play. Okay, so in Chapter 3, we first introduced hypothesis testing, and we used a permutation test to test a hypothesis, all right? So now we're going to examine hypothesis tests further, and we're going to look at a few different scenarios. We're going to look at means and proportions for one population. So is the mean equal to this, or is it not equal to this, or the proportion of success equal to this or not? We're going to look at bootstrap t-tests, and then we're going to look at means and proportions for two populations and sort of asking, are these two means or proportions the same or not the same? Okay. We're also going to pick up some related ideas. And if you've had a statistics class in high school, like AP Stat or something, some of these words will be familiar to you. Like we're going to look at type 1 and type 2 errors. We're going to figure out how to interpret test results. We're going to learn about the likelihood ratio test, which is incredibly useful. And then just some general thoughts about statistical practice. Okay. All right. So again, pause, copy, and play. So we're going to start with hypothesis tests for means and proportions in one population. And this video is going to mostly focus on means, and we'll do proportions in the next video. So let's look at an example of something we already know how to do, right? So an exam is given nationwide to all high school seniors, and this exam's been given a lot, so we know that the scores are going to follow a normal distribution of a mean of 515 and a variance of 116 squared. Okay. Now, on the blessed island of Sodor, there's 25 high school seniors who take the exam, and they have an average of 555. So this is a sample average because there's only 25 of them, right? And we'll just assume that their standard error or their standard deviation matches the nationwide of 116. So given that, we'd like to know whether we have statistical evidence to conclude the claim that Sodor seniors are above average. Okay, looks like they've scored above average. Does the data really back that idea? Okay. All right, so let's let mu be the true average exam score of Sodor seniors, so their true actual ability level, right? The null hypothesis, and again, let me remind you, in the null hypothesis, we are very conservative in changing our mind. So the null hypothesis would say, no, Sodor seniors are like nationwide seniors. So we assume their mean is 515, which would match the nationwide data. And the alternate hypothesis is, well, no, actually the Sodor average is above 515, okay? Because it looks that way. Okay, now, under the null hypothesis, a sample average of a normal distribution. So this is independent of the null hypothesis, but in general, if your data is from a normal distribution, a sample average will still be normal. Okay, this is a math 313 thing. It's like the central limit theorem, but since x1 up through xn were normal, their average is still normal. So under the null hypothesis, X bar would be normally distributed and it would share the mean of the original population, and it would not have 116. What would it have? 116 squared over 25. 25, yes. My bad there. Okay. All right, we've done that calculation a lot, doing the expected value of x1 up through x25 divided by 25, drag out the 25, blah, 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 do the same thing with variance. So we've done that a lot. All this is to say that if you take x bar minus the mean divided by its standard deviation, you have an N01, okay? All right, so let's go for a p-value. So the p-value is the probability of seeing a score as extreme or more extreme than the sample data. So in the sample data, we saw a score of 555, and our alternate hypothesis is strictly greater than 515. So the p-value is what's the probability the sample average could be greater than or equal to 555. So it is a one-sided p-value, okay? So under the null hypothesis, I can subtract the mean of 515, and divide by the standard deviation of 116 over root 25. And that will create a z value on the left, cranks out to 1.724 on the right. And that's N01. So the probability that z is greater than 1.724 is 1 minus the CDF evaluated at 1.724 for the standard normal distribution. And that turns out to be 0.043, which if 5% is our bar, is certainly less than 5%. So this would indicate that there's mild, I mean, it's close to 5%. So there's mild statistical support for the idea that SOTR students are smarter than average. Because again, this is telling us that a score of 555 or higher could occur by chance. The probability that that could occur by chance is about 4.3%, which we have decided is too low to consider reasonable for it to occur by chance. Thus, this assumption could not be correct, and we have to lean towards our ultimate. Okay, in that last example, the variance was known, right? So it was a normal distribution. We knew the variance. Everything was good and happy and known, all right? So then the question becomes, well, what happens if you don't know the variance? And we've told this story before. If we don't know the variance, then maybe there's this t-distribution, which is vaguely normal, that can really help us out. So why don't you pause, copy, and play? All right, so if in our data we don't happen to know our sigma, our standard deviation, or the variance of our normal distribution, we've got this t-test for a normal mean. So our data, our random samples, come from a normal distribution, but I don't happen to know the mean or the variance, okay? I am testing a value of the population mean. So my null hypothesis is the population mean is some mu sub 0, and the alternate hypothesis is that it's not, or maybe that it's greater than or strictly less than. Maybe it's a one-sided, this is pitching it as a two-sided, okay? The way this t-test is gonna work is I'm gonna calculate that t statistic that we've seen before. I'm gonna take my sample average from my data, subtract that null hypothesis mu sub 0, and then divide by S over root n. I don't have sigma, so I'm gonna use S, the sample mean of my data, in place of sigma, right? And X bar is the sample mean of my data. Sorry, S is the sample standard error of my data, okay? Now, under the null hypothesis, this test statistic has a t-distribution. It's vaguely normal. It's a t-distribution with n minus 1 degrees of freedom. And then the p-value, as always, is the probability of the test statistic being as extreme or more extreme than the observed value of that t-statistic, okay? So this t-statistic is part of the t-distribution, and I want to know the probability that the t-distribution can be as extreme or more extreme than that observed test statistic, okay? So let's do it via an example. We've got a coffee vending machine. So you put in your coins. There used to be these metal little discs that had images on them, and you place them into machines, and it would dispense things for you. It was a wonderful time. So we got a coffee vending machine. It should pour out a 7-ounce cup of coffee for you, okay? And we want to test whether this is actually working properly. So let's let mu be the true amount dispensed. And we'll assume that the amount dispensed is normally distributed, but I have no clue what the variance is or the mean, okay? Null hypothesis is to assume it's doing its job. So we'll assume mu is 7. Alternate hypothesis, for some reason, it's going to be a one-sided. We'll assume mu is less than 7. All right, so what we're going to do is we're going to measure 15 cups of coffee. So we're going to get the machine to dispense 15 cups of coffee, okay? We measure the amount of coffee in each cup and take the sample average and get 6.6 ounces. And we take our sample standard, we calculate our sample standard error and get 0.8 ounces. Okay, and let's now determine the p-value. Okay, well, let's calculate our observed test statistic. There's my X bar minus my mu sub 0 over my S over the square root of n, and I get negative 1.9364. And I am looking for the ability for how likely is it for the t variable to be as extreme or more extreme than this guy. And since it's one-sided, I'm just going to look for the t value to be less than or equal to that number. So my p-value is the probability that the t random variable can be less than or equal to negative 1.9364. Now this random variable follows a t distribution with 14 degrees of freedom. So I'm going to have R compute that probability for me. And the command is P to the CDF. I don't know why. CDF of a t distribution. Calculate the probability at or below negative 1.9364, and the t distribution has 14 degrees of freedom. So that is what I typed into R, and I got 0.0366. That's less than 0.05. So that suggests the machine is underfilling the coffee cups. I will reject my null hypothesis, okay, because this is saying there's about a 3.6% chance that this data occurs by chance if the null hypothesis is correct. That seems unlikely, so let's go with the alternate hypothesis. All right, last panel, some wrap-up thoughts on this, which should sound familiar. So why don't you pause, copy, away we go. So that t distribution is vaguely normal. And in the last time we encountered this, we talked about when we can use the t distribution. And so we're going to do the same thing here. So when can we use this for the testing a normal mean? Now, for this test that we just did in the last panel to give the exact p-value, the sample, the data we had must have been from a normal distribution. Okay, then it's perfect, great, no problems. If our data is not normal, the t-test may still give a good approximation of the p-value if the variance is finite, and as our sample gets larger and larger, the distribution of our test statistic approaches a real t distribution, okay? Which is to say, in general, if the distribution of our test statistic is not too skewed, and if n is large, the t-test provides a decent approximation of a p-value, okay? So before we said the t distribution works great for normal data, but if your data is not normal, as long as it's vaguely symmetric, it still works great. That's essentially what we're saying with these 2 points here, okay? Now, if your data is not normal, as a statistician, it's a good idea to check your p-value by calculating the p-value via a permutation test or a bootstrap t-test, okay? As well as the t-test for normal mean. If your results vary, and by the result, I mean whether or not you accept or reject the null hype, if that varies based on these 2 tests, don't use the t-test, okay? Because clearly you were too far away from being normal or symmetric for the t-test to work well, right? And then also it's a good idea to conduct these t-tests with your outliers and without your outliers to see if that makes a difference. And if it does, then maybe you kick out your outliers, but you tell your audience that you have removed the outliers.